So one of the interesting things about a multi-tool, whether it's kind of the DeWalt saw or the Leatherman or even the cell phone, is that they all have limitations. I mean, I'm guessing you all love your cell phone, but you probably would rather not type a term paper on your cell phone. You could, but it's not really the ideal purpose. Like my multi-tool here is really good for making very short cuts, right? It's got this nice little blade and can get in all kinds of weird spaces, but it's not very good if I want to, build a bookshelf. It's good for like making those really funky cuts and trying to customize things. And so just like there are limitations on those multi-tools, there are limitations on the Power Series. Specifically, Power Series don't work everywhere. The areas where they work, we call the interval of convergence. The width of that interval, we call the radius of convergence. And where those Power Series fail, those Power Series representations fail, we say that the Power Series diverges. So in this section, while we've hinted at it earlier, in this section, we're going to take a deep dive into where Power Series converge of power and potential in this world of Power Series. Once again, these Power Series, these are like the duct tape, the Swiss Army knife of mathematics. All right, so one question that students have is, what do we need to memorize? So there's 3 Maclaurin series that I want you to memorize. The first one is the one we've been using from the recently, the e to the x Maclaurin series. The second one I want you to have memorized is the Maclaurin series for sine x that we derived earlier on in the section. And third, I want you to have memorized the cosine Maclaurin series, which you may remember as one of the examples we did back in, I think, the very first lesson, maybe on page 2 of starting to talk about Power Series. In case you're trying to remember which is which, you can always, substitute in some upper bound and just graph it on your calculator. But it's interesting to note that sine is an odd function. It's symmetric about the origin. And notice that the sine has all of those odd powers of x and odd factorials. So everything about sine is odd. And similarly, cosine is an even function, symmetric about the y-axis. And you can see that all of those factorials, all of those powers are even powers. So it sort of gives you a new meaning of this idea of an odd function and an even function. When you see, oh, an odd function has only odd powers, an even function has only even powers, that's pretty crazy. Continuing on. If you've been paying attention, you may have noticed that we've found power series in the previous few examples, but have not made mention of where these series are valid. This is because we are no longer working with geometric series, and consequently, we need more power. That is a pun. So specifically, to figure out where these series are valid, where they converge, what we're going to later call the interval of convergence, we need 2 facts and 1 method or test. So fact 1 is that the harmonic series diverges. You might say, what is the harmonic series? The harmonic series is the series of the sum of all the 1 over n's. Notice that here we have to start at n equals 0, so we don't divide by 0. Dividing by 0 is undefined. So it diverges, the sum is equal to infinity. What are we saying here? We're saying that 1 plus a half plus a third plus a fourth plus a fifth plus dot, 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 dot. If we add up an infinite number of these fractions, even though they get smaller and smaller and smaller and smaller, this is going to equal infinity. So that's fact number 1. You will, at the moment, I'm just stating it as a fact. In a later course, you'll get to see why, or we will prove why this is the case. But at the moment, I'm just telling it to you. I would be happy to take it offline if you want a proof of it. Fact 2 is that the alternating harmonic series converges, that is, equals a number. In symbols, we would say that the sum from n equals 1 to infinity of -1 raised to the n plus 1 power over n equals a number. It happens to be equal to the ln of 2. The ln of 2 part isn't important. Like, this is not important, at least for our purposes. Important. What is important is that it converges. So what does this mean? This means that, so if I put in n equals 1, I'm going to get a positive 1 out. So it means 1 minus 1/2 plus a third minus a fourth plus a fifth minus a sixth. So you've got the signs are changing, but it's the same series as above, but now the signs are changing. If I continue on in this path forever, I would say that this converges. It equals a number. Okay. So that's fact 1 and fact 2. So why does one infinite series converge and another diverge? That is a big question, and we're going to leave it for another course. However, we can see that sometimes we sum an infinite number of terms and get a number, that is, it converges, and other times we sum an infinite number of terms and we don't get a number, it diverges. One of the most powerful ways of determining if a series will converge is to ask, do the terms decrease fast enough to converge? That's great, but how do we measure fast enough? So in example 4, we're going to explore the ratio of consecutive terms on these 3 series. So we want to look at the ratio of consecutive terms on these 3 series, the first of which is 2 times 1/3 to the n. You'll recall that this is a geometric series. Pardon me. It's a geometric series. And it converges. And we've already worked with this. The sum from n equals 0 to infinity would be the leading coefficient, which is, so this is 2, pardon me, gotta get my work together. 2 times 1/3 to the n will be 2 divided by 1 minus 1/3, which works out to be 3. So it converges to 3. But for our purposes, what I want to point out is that this thing is equal to, it looks like 2 plus 2 times 1/3 plus 2 times 1/3 squared plus 2 times 1/3 cubed plus 2 times 1/3 to the 4th plus dot, 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 dot. Okay, so that's what my series looks like. And what I'm going to do is I'm going to look at consecutive terms. So consecutive terms such as, it doesn't matter which ones, but maybe I'll look at these 2 terms here. And so I'm going to look at the ratio. Ratio means division. So I'm going to look at the ratio of the second of the highlighted terms divided by the first. So look at the ratio. And in this case, the ratio is going to be 2 times 1/3 to the 3rd power divided by 2 times 1/3 to the 2nd power. And notice this ratio is equal to 1/3. Okay, that's great. What if we tried a different combination? What if we looked at the next 2 terms out, the blue terms? Well, in this case, again, we would look at the ratio of the second term, okay, here. And so our higher power would be a 4 divided by the first term, or the previous term, here, which would have a power 3. And again, you can see in this case, for the second time, the ratio of the 2 is 1/3. So, and you could you can see that this would continue on regardless of how far up we went in the series. So what you'll notice is that if we looked at the ratio of an plus 1, and we divided it by an in this case, so in the highlighted case, so if n was equal to 3, that would give you, this is interesting. So I've got to back up on my vocabulary. So an represents the nth term in the sequence. It's sort of like cn, but cn is just the coefficient. So an is the whole term. So in this particular case, in working on my vocabulary, a naught would be 2, a1 would be 2 times a third, a3 would be 2 times a third squared, a4 would be, I said a1. It would be a naught is 2, a1 is 2 times a third, a2 would be 2 times a third squared, a3 would be 2 times a third cubed, etc., etc. So in this case, the an, like in this particular case, our n would be 3. So a3 would be 2 times a third cubed, and then a n plus 1, n is 3, so a 3 plus 1, or a 4, would be the 2 times a third to the fourth. And in each of these cases, we got a third. So note what we're saying is that if you look at those consecutive terms, it looks like the yellow one, the later term divided by the earlier one, the green term, okay, has a ratio that's always a third, or specifically it's always less than 1. Okay? And because it's less than 1, that means our series is getting small very, very quickly. They're decreasing by about a third every single time. So that's the A series. Or I should say, example 1, the geometric series. Let's do the same thing with the harmonic series. So if we do the same thing with the harmonic series, notice this is equal to 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, et cetera, et cetera, et cetera. So let's look at some consecutive terms. So if we look at some consecutive terms, say 1/2 and 1/3, and we're going to take the ratio, the second term is going to go in the numerator, 1/3, divided by the first term, in the sequence, 1/2. And altogether, this would be the same as, looks like 2/3. Okay. And then maybe we could look at some later terms. Suppose we look at these green ones. So here, we'll look at the second term, 1/6, and we divide by the first term, 1/5, and this simplifies to 5/6. You could look at this pattern and realize that what's going to happen is as we continue on, we're going to keep going, dot, dot, dot. At some point, we're going to have a 1/n plus a 1/n plus 1 plus dot, 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 dot. And so if we looked at those terms, you could see that you would get 1/n plus 1, 1/n plus 1 divided by 1/n, which is equal to n/n plus 1. And notice that as n goes to infinity, n/n plus 1 equals 1. So that tells what that tells us is that our terms are not decreasing fast enough for us to know, using this approach, whether or not the series will converge or diverge. We happen to know that this particular one diverges. We could do this same thing on the alternating harmonic series, and it would also equal 1, but we would know it actually might equal -1, but it would converge. And so you can see that if it equals 1, sometimes it converges, sometimes it diverges. It's not going to converge fast enough for us to have the kind of information that we want. So in C, again, we're trying to understand something about how fast a series, like how fast the terms in a series shrink. So we can write out some of these terms, pardon me. So here we actually have a power series with x's involved. And so this will be like 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus dot, 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 dot. And again, we could ask what happens if we look at the ratio of consecutive terms. That is, how fast are these terms approaching 0? So if we looked at those first 2 terms, we would divide, take the top term, x cubed over 3 factorial, and divide by x squared over 2 factorial. And this is going to equal x over 3. Or maybe we could look at the x to the 5th and x to the 6th terms. Here, this would give us x to the 6th over 6 factorial divided by x to the 5th over 5 factorial, which simplifies to x over 6. And so I think it should be reasonable to see that if we continue this out, we plus dot, 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 eventually we're going to get to an x to the n over n factorial plus x to the n plus 1 over n plus 1 factorial plus dot, 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 dot. And so if we looked at those 2 terms together, we would have x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial, which simplifies to x over n plus 1. This stuff up here is from a previous example. And what I want you to see here is that as n goes to infinity, as long as x stays fixed for a fixed value of x, we know that x over n plus 1 will go to 0. That is, once again, the consecutive terms get smaller and smaller and smaller. They shrink very, very rapidly relative to each other. The ratio of the 2 gets smaller and smaller very, very fast. And so when they shrink quickly, when this ratio goes to a number less than 1, we're going to get convergence. When this ratio is 1, it's going to be inconclusive. It can kind of go either way. When the ratio is greater than 1, we're going to get that's going to diverge. And this is a little bit of an exploration of a concept or a test that we're going to call the ratio test, which we will introduce in the next section. A deep dive into where power series converge. If you've been paying attention, you may have noticed that we found power series in the previous few examples, the previous lessons, but we have not made mention of where these series are valid. This is because we're no longer working with geometric series, and consequently, we need more power, kind of a pun. Specifically, we're going to need 2 facts and 1 method or test. Let's start with the facts. Fact number 1, the harmonic series diverges. In symbols, the sum from n equals 1 to infinity of 1 over n equals infinity. This series right here is called the harmonic series. It's worth knowing. It's worth knowing its name, and it's definitely worth knowing that this series diverges. So what does that look like if we spell it out? That sum from n equals 0, sorry, not 0, but 1, so we can't divide by 0, from n equals 1 to infinity of 1 over n would be 1 plus 1 over n. Oh my gosh. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, 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 dot. And if you add up these small fractions, even though they're getting smaller and smaller and smaller and smaller, if you add them all up, eventually you will get infinity. That is, the series diverges. Harmonic series diverges. The actual proof of this will have to come in another class. I'd be happy to talk about it in some other time in some other video, but for the moment, we'll just take it as a fact. Fact 2, the alternating harmonic series converges. In symbols, that'd be the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n equals the ln of 2. I don't actually care that it's the ln of 2. What I really care about is that it converges. That is, it equals a number. So here, the alternating harmonic series, again, a name you need to know, which is this thing over here, converges, equals a number. If we were to spell that out so you could see it, that would be the sum from n equals 1 to infinity of negative 1 to the n plus 1. The little power of n plus 1 is to get the signs to line up right, over n. So this will be 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6, etc., etc., etc. If you add up all of these terms where they have the alternating signs, hence the alternating harmonic series, you will get out a number, a fixed constant number. So why is it that one series converges and another diverges? That's a really big question. And actually, we're going to have to leave it for another course. However, we can see that sometimes if we sum up this infinite number of terms, so here's our infinite number of terms that we're adding up, sometimes we add that up and we get a number like we do with the alternating harmonic series. Here we get a number, and other times we don't get a number. That is, it diverges. So what's going on here? One of the most powerful ways of determining if a series will converge is to ask, do the terms decrease fast enough to converge? That is, are the terms getting small, but getting small fast enough that when you add all these things together, you get a single number? That's a great question, but it leads to a follow-up question of how do we measure this idea of fast enough? So what does that mean? We're going to use the idea of a ratio to try to figure out what it means for something to converge fast enough. Example 4, explore the ratio of consecutive terms on these series. So let's start with the geometric series, the sum from n equals 0 to infinity of 2 times 1/3 to the n. That would be 2 times a third to the 0, plus 2 times a third to the 1, plus 2 times a third to the second power, plus 2 times a third cubed, plus 2 times a third to the fourth, plus dot 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 dot, plus 2 times a third to the n, plus 2 times a third to the n plus 1. And so if, for example, we just looked at the first couple of terms here, and we looked at the second term, which is 2 times a third to the first power, and we divided it by 2, the previous term, 2 times a third to the 0th power, everything is going to cancel except for one factor of a third. We could try this again later on. Maybe we could look at the third power and the fourth power terms. So if we look at the, so I've got a pair of terms, consecutive terms, and I'm going to take the second one and divide by the earlier one. So again, 2 times a third to the fourth divided by 2 times a third cubed will again be 1 over 3. Same ratio. That's why for a geometric series, we talk about there being a common ratio. Let's do this one more time. So if we look at this n plus 1 in nth terms, so this would be 2 times a third to the n plus 1 divided by, and then we take the term before it. So it's the second term divided by the first term. So 2 times a third to the nth. And once again, we see the 1/3. Here again, you have the same fraction each time, the common ratio. And that's one of the distinctive, or maybe the distinctive characteristic of a geometric series. Anyway, it appears that as n goes to infinity, the ratio of these consecutive terms approaches 1/3. The limit of these terms appears to be approaching 1/3. Not only does it appear to be approaching 1/3, it seems like it's always 1/3. Okay, and we happen to know from our other work that this series converges. So it converges and approaches 1 over 3. B, the sum from n equals 1 to infinity of 1 over n, that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus dot 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 plus 1 over n plus 1 over n plus 1 plus dot 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 dot. This series has a name. Once again, this is that's right, the harmonic series. You need to memorize that. This is the harmonic series, and I hope you remember that this thing diverges. Diverges. All right, so we're going to play the same game as before. We're going to look at consecutive terms. So maybe I will look at the first two terms. I have 1 over 2 divided by 1 over 1. And if I simplify, this is going to be 1 over 2. If I look at some later terms, this would be 1 over 5 divided by 1 over 4, which is 4 over 5. Or more generally, if I look towards the end, at the nth and the n plus 1th term, this would be 1 over n plus 1 over 1 over n, which simplifies to n over n plus 1. And so notice that it appears as n goes to infinity, n goes to infinity, n over n plus 1 is approaching 1. So the ratio of consecutive terms approaches it approaches 1. So notice here we approach 1 and the series diverges. C, the sum from n equals 0 to infinity of 2 times 3 to the n, that is 2 times 3 to the 0, plus 2 times 3 to the first, plus 2 times 3 to the second, plus 2 times 3 to the third, plus 2 times 3 to the fourth, plus dot, 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 plus 2 times 3 to the n, plus 2 times 3 to the n plus 1, plus dot, dot, dot. Here again, we have a familiar series. This is the geometric series, once again. And notice that this is, I hope, quite clearly a divergent series because we're adding bigger and bigger things each time. So we can see even before we start that this thing is going to diverge. But we're talking about divergence, but specifically we're talking about ratios here. So let's not miss our plan. So if we look at those first two terms and we divide the second term, 2 times 3 to the first, divided by 2 times 3 to the 0th, everything cancels except for a factor of 3. We look at terms 3 and 4. That's the first, it's assuming we start at 0. This would be 2 times 3 to the 4th divided by 2 times 3 cubed, which is again 3. Oh, wait, same number, geometric series, common ratio, just like we talked about earlier. And then keep it on going. We expect it to be 3, but let's just verify. So we'd have 2 times 3 to the n plus 1 divided by 2 times 3 to the n. And sure enough, it's 3. Once again, you have this common ratio, which is the single most important defining characteristic of the geometric series. That is that the ratio of consecutive terms is constant. So it appears that as n goes to infinity, the ratio of the consecutive terms is 3. It approaches, it actually is 3, but I'm going to just write approaches even though it is. So it approaches very closely. Approaches 3. And we notice that it approaches 3, and again, the series diverges. Why would this be the case? So if the common ratio is 3, that means every term is 3 times bigger. So it means each term is bigger than the last. So when this term over here on the end is bigger than 1, that's telling us that the terms are getting bigger. When that term is less than 1, it's telling us that the terms are getting smaller. And when it's equal to 1, it tells us that the terms are about the same size. Maybe they're getting bigger, maybe they're getting smaller, maybe they're getting smaller really fast, maybe they're getting smaller really slowly. Don't know. That's where we are so far. D, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n, that is 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus dot, 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 plus minus 1 to the n plus 1 over n, plus negative 1 to the n plus 1 over n plus 1, plus dot, dot, dot. You, I hope, recognize this as the alternating harmonic series, which we know from fact number 2 converges. Okay, we're going to play our same game, but there's one little piece of fine print that we've got to address here. So here we're going to have minus 1/2 divided by 1 over 1. So that would be over 1 over 1. Sorry, I've got a typo here. 1 over 1, which would be minus 1 over 2. And then we look at the next terms out. So I'd have 1 over 5 divided by, it's a little hard to see there, but there's a minus sign. So I have minus 1 over 4. And so this will be negative 4 over 5. And then if we look at these terms out here, I think you can see the pattern. You might not know which was the positive and which is the negative term, but certainly in the ratio, you're going to have a negative 1 over n plus 1 over 1 over n. We're not sure whether the numerator was the negative term or the denominator was the negative term, but we know that one and only one of them was negative, so it's okay to leave it this way. This would be negative n over n plus 1. Okay, so before we go on, let's talk about these negatives that are here in our ratios. We actually really don't care about those negatives. What we care about is whether this number is bigger than 1, equal, or is approaching 1, is approaching something bigger than 1, or is approaching something less than 1. And so what we're going to come through here and do is we're going to say, as far as our ratios are concerned, we care about the absolute value. And so in absolute value, notice our terms will always be positive. And so it appears that this negative n over n plus 1 in absolute value is also approaching 1. It approaches 1. So here we're getting 1. And again, it's 1. And this time it converges. If you look back up and you compare this to example B, notice in the case of B, the limit approached 1, but we diverged, whereas in D, it approached 1 and we converged. And we'll talk more about this later. Last example for this exploration. So again, we're going to look at consecutive terms. So if I look at those first couple of terms, I'm going to get x over 1. Then if I go a little farther, I would get x to the 4th over 4 factorial divided by x to the 3rd over 3 factorial, which simplifies to the x's are going to cancel. So you're going to end up with a x times a 3 factorial divided by 4 factorial. And if you remember your factorial rules, you'll remember that this would be equal to x over 4. And then if we look at those last two terms, we can do the same thing. So we know we're going to have x to the n plus 1 over n plus 1 factorial. Remember to put your parentheses around the n plus 1 factorial divided by x to the n over n factorial. And I hope you could see what happens here. You're going to end up with an x over n. So here's our pattern. You had a 1 in that denominator, a 4 in that denominator, an n in that denominator. In each case, that 1 was coming from the x over, like x over 1. And 4 was coming from x to the 4th over 4 factorial. So that was the 4 that was there. And here I should have an n plus 1. Caught my own error. N plus 1. So we also remember from the previous example that what we care about is the absolute value of this stuff. And so it appears that as n goes to infinity, the ratio of the consecutive terms approaches x over n plus 1 in absolute value. And this is a little bit interesting. Notice here that this would be equal to 1 over n plus 1 times the absolute value of x. And x, as far as this n going to infinity is concerned, that's only impacting the n. X is a constant. And so this n plus 1 is going to go to 0, and the x is remaining constant. So the ratio of the consecutive terms approaches 0. So here, we're going to approach 0, and we know that this series that we're working with converges to e to the x, although we're not quite sure when. So we're not 100% sure at this point what to make of this 0. So there's a kind of a question mark that goes with this. Unlike the other examples where we knew what it meant, here there's an x and we're not quite sure what that all entails. But there we have some examples to show us how we would calculate ratios and you get the sense that sometimes that ratio might tell us when we converge, sometimes it might tell us when it diverges, other times it might not be able to tell us anything at all. So let's sum up what we've seen about series and ratios thus far. So let's start off by talking about the power series coefficients and terms. So a power series has this form, the sum from n equals 0 of c of n times x to the n equals c naught plus c1x plus c2 x squared plus c3 x cubed plus dot 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 plus cn x to the n plus cn plus 1 x to the n plus 1. And I want to give a little bit of vocab here. We call this c naught, we call that the whole thing a naught. C1x, that's our a1. C2x squared, that's our a2. So C3x cubed, that's our a3. Cnxn, that's our an. Cn plus 1, xn plus 1, x to the n plus 1, that's our an plus 1. And so the key is that the a's, these guys right here, they include the x's. Include the x's, whereas the c's have no x's in them. So we just about said it here. We said that the coefficients are the C naught, C1, C2, C3, et cetera, et cetera. Those are the numbers here. And they have no x's in them. The terms are a naught, a1, a2, a3, da 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 da, an plus 1. That's these guys. And these include the x's. So 2, about ratios of consecutive terms, an and an plus 1. So like we talked about previously, if a ratio is bigger than 1, in the previous, we had an example where it was 3, for example, that means that the terms are increasing rapidly each time you multiply by 3 in the example on the previous page. In B, ratios less than 1 mean the terms are decreasing to 0 rapidly. We had a geometric series example where the common ratio was 1/3. That meant every term was 1/3 the size of the previous one. These terms are getting small very, very fast. And finally, if the ratios are about 1, that means things aren't changing quickly enough to know how to draw a conclusion. That is, to draw a conclusion using the ratios. In one of our examples where that ratio approached 1, the series converged. That was the alternating harmonic series. In the other case where the ratio approached 1, the series diverged. That was our harmonic series. So we had a little bit about absolute value in the last section. And so the deal is that terms can vary in sign, positive or negative, or sometimes, as in example E, we had an X in our answer. And so we didn't know whether X was positive. So the absolute value of the ratio makes quantities bigger, positive. Sometimes it doesn't change them at all if they're already positive. And thus, since it makes everything bigger, it can only make convergence more difficult, like the same or more difficult. So if a series converges with that absolute value, it certainly is going to converge without it. And so when we add that absolute value, it gets rid of this confusion bit, only makes convergence more difficult, and this gives us a more powerful result in the cases where it does actually tell us conclusively that a series converges or diverges. This leads us to a powerful, very powerful, and relatively easy test for convergence. Definition, the ratio test. A, if the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to L, that is a number, a fixed number, which is less than 1, then the sum from n equals 0 to infinity of an, which is equal to the sum from n equals 0 to infinity of Cn x to the n, is absolutely convergent. We haven't talked about what absolutely convergent is versus convergent, but for the time being, just know that it works all the time. B, if the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to L, which is bigger than 1, then the series from n equals 0 to infinity of an, which is equal to the series from n equals 0 to infinity of cn times x to the n, is divergent. So bigger than 1, divergent, less than 1, convergent. If the limit is n goes to infinity of the absolute value of an plus 1 over an equals 1, then the ratio test is inconclusive. So what am I trying to highlight here? We're looking at the ratio of consecutive terms. And when that ratio is less than 1, then it's convergent. When it's bigger than 1, then it's divergent. And when it's equal to 1, the test is inconclusive and you need to do something else. Try again. I encourage you to review the questions on the previous page. Notice how they provide examples of the ratio test at work. In particular, notice that when the ratio approaches 1, this can mean either convergence or divergence. That is why we call the test inconclusive in this instance. So be very careful of when the ratio test is equal to 1. You don't want to draw a conclusion when you shouldn't be drawing a conclusion. Example 4. Where does the Maclaurin series e to the x equal to the sum from n equals 0 to infinity of x to the n over n factorial converge? So we're going to answer this using the ratio test. So let's start with our ratio test. So that would mean we need to look at the limit as n goes to infinity of the absolute value of the ratio of the consecutive terms, an plus 1 over an, which would be the limit as n goes to infinity of, now here we got to work a little harder. So it'd be x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. And I hope you recognize this as the same ratio we had in one of our previous examples. So this is equal to the limit as n goes to infinity of x over n plus 1, all in absolute value. Now, remember that as far as the limit is concerned, the only variable that's changing is the n. X is considered a constant for the purpose of our question. So you have a constant, a number, x, 2, 7, pi, 10 zillion, doesn't matter. But then we're dividing it by n, which is going to infinity. And this is equal to 0. So we get that the ratio test gives us 0, and it's 0 regardless of what x is, so for all x. So that tells us that our series converges for all x, for all values of x, all values of x, that is from negative infinity to infinity. Example 5. Consider 5 over 4 minus x, which is 5 over 1 minus negative 3 minus x. It has geometric series, the sum from n equals 0 to infinity of 5 times negative 3 minus x all raised to the n, which is equal to the sum from n equals 0 to infinity of 5 times negative 1 to the n times 3 plus x to the nth power. Find the x values where this series converges using the ratio test. There's actually a whole bunch of work shown here. I show this work because this is an unusual representation for this particular geometric series, and so I wanted to explain where it came from. But at the end of the day, all we really need to do is use the ratio test on this series here at the end. So we're going to use our ratio test. And so when we use our ratio test, we're going to look at the limit of the consecutive terms. So that will be absolute value of an plus 1 divided by an, which will be the limit as n goes to infinity of absolute value 5 times negative 1 to the n plus 1 times 3 plus x to the n plus 1 divided by 5 times negative 1 to the nth over 3 plus x to the nth power. And you'll notice that some of these terms are just going to cancel. The 5s cancel. The absolute value is going to kill the negative 1 to the powers. It doesn't even matter how those simplify. And we're going to be left with the limit as n goes to infinity, just the absolute value of 3 plus x. Now, we know that this series is going to converge when this is less than 1, converges by the ratio test when the absolute value of 3 plus x is less than 1. That is, when negative 1 is less than 3 plus x is less than positive 1, or if we subtract 3 from each part, that would be when negative 4 is less than x is less than negative 2. And so the series converges between negative 4 and negative 2 by the ratio test. You might ask what happens at negative 4 and at negative 2, because at those places it would be 1. In this particular case, it's a geometric series, and I think it should be a little bit clear. So if we test x equals negative 2, so if you test x equals negative 2 by putting it into this expression, you'll get a 3 plus negative 2. That would be you're going to get a positive 1 to the nth power. And so you're going to just be adding a whole bunch of, in this case, 5 minus 5 plus 5 minus 5 plus 5 minus 5 plus 5 minus 5. And so it would diverge in that case. Because it'll be 5 plus 5, 5 minus 5, 5 plus 5. So that's 1. If we test the other endpoint, x equals negative 4, then we would be putting in the negative 4 in place of the x. So 3 plus negative 4 would be negative 1 to the nth power. So you have negative 1 to the n times negative 1 to the n. That would be positive 1 to the n. And you have 5 plus 5 plus 5 plus 5 plus 5. Certainly that is also going to diverge. So even after testing our endpoints, our series still converges quite nicely between negative 4 and negative 2, not including the 2 endpoints. So as we focus in on convergence, 2 definitions will help us. Definition, the interval of convergence. So the interval of convergence of a power series is the interval that consists of all values of x for which a series converges. Note, intervals have endpoints, like we talked about above, that may or may not be included in the interval of convergence. Next, a lazy definition. This isn't quite as precise, but the radius of convergence is half the width of the interval of convergence. It's possibly 0, it's possibly infinity. So let's go back to example 5, considering 5 over 4 minus x, which is the sum from n equals 0 of 5 times negative 1 to the n times 3 plus x raised to the nth power, and find its interval of convergence and radius of convergence. Well, good news, we already found its interval of convergence. I'm going to call that interval of convergence the IOC interval of convergence. And we already found that to be negative 4 less than x less than negative 2. Or if you like, if you prefer, negative 4 to negative 2. The radius of convergence, which I'm going to abbreviate with radius of convergence, ROC, not to be confused with rate of change, is going to be given by R, number R, and it's going to be half the width of the interval of convergence. So notice up here that this width is equal to 2, right? The distance between negative 4 and negative 2 is positive 2. And so my radius of convergence is going to be 2, this same 2 right here. Another color. This 2 is the same as that 2. And then I'm going to divide it by 2. And that 2 is because of the half the width part. So my radius of convergence is going to be 1 in this case. The following examples show how we find the interval of convergence and radius of convergence once we have a power series in hand. So example 6. Suppose you're given a power series, the sum from n equals 1 to infinity of x to the n over n times 3 to the n. Find its interval of convergence and radius of convergence. Just a brief note, in this particular case, notice that the series starts at 1, and sometimes it starts at 1, sometimes they start at 0. Here we can't start at 0 because that would put a 0 in the denominator in the very first term. And so in the context of convergence, the initial terms don't make any difference in whether the series will converge or diverge. And so this series could start at 1 or 10 or 100 or 10 million. In any of those cases, we would have the same interval of convergence and radius of convergence. All right, back on track. So let's find our interval of convergence. We're going to use our test. So we're going to start with the ratio test. So if we to start with our ratio test, we need to look at the limit as n goes to infinity of the n plus 1th term divided by the nth term. So maybe I won't write the formula this time. So it'll be x to the n plus 1 divided by n plus 1 times 3 to the n plus 1, all divided by x to the n over n times 3 to the n. So this will be equal to the limit as n goes to infinity of absolute value of, looks like we have x times n over, I think we've got 3 times n plus 1. And you'll notice that as the only thing changing here is the n. And so as n goes to infinity, n over n plus 1 will approach 1. So this whole quantity will approach the absolute value of x over 3. Okay. We want this to converge. So again, we're using the ratio test. So we need to solve for where the absolute value of x over 3 is less than 1. This would be where absolute value of x is less than 3, or between -3 less than x less than +3. Now, notice that this tells us where we converge absolutely. We're not sure what's happening at our endpoints. So we still need to test the 2 endpoints. So we're going to test, maybe I could start with test -3. So test x equals -3. When I want to test x equals -3, what I do, I said it aloud earlier, but I didn't actually do it. Here, what I'm going to do is I'm going to substitute that -3 back into the original sum and just see what I have. So our original sum will now look like the sum from n equals 1 to infinity of x is going to be replaced by -3. So I have -3 to the nth power over n times 3 to the nth power. Now you'll notice there's a 3 to the n over, or -3 to the n over 3 to the n. So this will be equal to the sum from n equals 1 to infinity of -1 to the n over n. This isn't exactly like what we had before, but this is very, very close. It's just off by a sign to our alternating harmonic series. So this is an alternating harmonic series, and so this puppy converges. Okay. So now, that was when we tested it, x equals -3. So now we're going to come through and we're going to test at +3. So let's test x equals +3. And so again, to do that, we just substitute x equals 3 into this original summation. So I have the summation from n equals 1 to infinity, 3 to the n, for n times 3 to the n, which would be the sum from n equals 1 to infinity of 1 over n. This is the harmonic series. This baby diverges. Like that. So we have learned that our series converges at x equals -3, it diverges at 3, it converges everywhere in between, and so we can state our conclusion. So our conclusion is going to be that our interval of convergence is going to go from including -3 to 3, but excluding 3. So I have the include the -3, exclude the +3, and of course include everything in between. And then our radius of convergence, our ROC, is half the width of this interval. So from -3 to 3 is 6. 6 divided by 3 is 3. So this up here, this is our conclusion from this particular question. Example 7. Suppose you're given a power series, the sum from n equals 0 to infinity of -3 to the n times x to the 2n over the square root of n plus 1. Find its interval of convergence and radius of convergence. In this particular case, we are not going to be able to find its interval of convergence using just the facts that we know here from this class. There's something that's a little bit beyond this class, but we'll be able to come close to it. We just won't understand what's going on with our endpoints. So anyway, we're going to dive in and use our ratio test. So we need the limit as n goes to infinity of the next term out, absolute value. So I have next term out, so -3 to the n plus 1 times x to the 2 times n plus 1 over square root of n plus 2 divided by the whole quantity, -3 to the n times x to the 2n over square root n plus 1, all in absolute value. Whew. Okay, let's write this one out a little bit more so you can see what's happening. This is n, limit as n goes to infinity of the absolute value of -3 to the n plus 1 times x to the 2n plus 2 divided by square root of n plus 2 times, invert and multiply, square root of n plus 1 over -3 to the n times x to the 2n. All right, notice the absolute value takes care of all the negatives, so we don't have to worry about that, but we do have to account for the fact that those are 3's. And so this whole thing is going to equal the limit as n goes to infinity of, we have a 3 to the n plus 1 over 3 to the n, ignoring the negatives, so there's going to be a 3 in our numerator. We have an x to the 2n plus 2 over x to the 2n, which would be x squared. And then we have a root n plus 1 divided by root n plus 2. The only thing the limit cares about is the n. And so the square root of n plus 1 over the square root of n plus 2 is approaching 1. And so all this stuff is approaching the absolute value of just 3x squared. we want to solve, we want to know when is this thing going to be less than 1. That's when the ratio test will work. And so we can divide by 3. This would tell us that the absolute value of x squared is less than 1 over 3. Or in other words, that the absolute value of x is less than 1 over the square root of 3. Or in other words, negative 1 over square root of 3 is less than x is less than positive 1 over square root of 3. We would like to check our endpoints, but the problem is if we're checking our endpoints, then we're going to end up with needing to know what happens to the sum of 1 over square root of n plus 1. And that requires convergence tests that we just don't have available to us at this time. It would turn out, if we were to go through all of this stuff, it would turn out that this series would converge on the positive side and diverge on the negative side, but we actually don't have that information. So, but we don't have enough information to determine the endpoints using the skills we've learned so far in this class. But what we can say is we can say that the endpoints are unknown, or specifically they're beyond us, But even if they're beyond us, we can see that the radius of convergence, ROC, radius of convergence, R, will equal half this width, which will just be 1 over the square root of 3. Example 8, find the interval of convergence and radius of convergence of the Maclaurin series sine x equals the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. It's going to blow your mind. We're going to start with our ratio test. So ratio test. So we need the limit as n goes to infinity of the absolute value of, now here's our ratio. So negative 1 to the n, x to the 2 times n plus 1 all over 2 times n plus 1 plus 1, all that factorial. Make sure you get your parentheses for your factorial. All divided by negative 1 to the n. Oh, I lost my plus 1 up here. X to the 2n plus 1 over 2n plus 1 factorial. Yeeks, that's ugly. So this would be the limit as n goes to infinity of the absolute value of negative 1 to the n plus 1, x to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial divided by negative 1 to the n, x to the 2n plus 1. Okay. The absolute value is going to kill the negatives. That part's easy. And the factorial simplify. So this is going to be equal to the limit as n goes to infinity of, we're going to have an x squared divided by, notice you have 2n plus 1 factorial upstairs and 2n plus 3 factorial downstairs. And so we've got 2 different terms we have to account for. So we're going to have 2n plus 3 times 2n plus 1. As far as the limit is concerned, the only thing that's changing is those n's. So x is fixed, whether it's negative 7, negative square root of pi, 15, 2 billion, whatever it is, it's fixed, and then you're dividing by bigger and bigger denominators. And so this limit is going to equal 0. And one of the amazing facts about 0 is that it is always less than 1. So this tells us that our interval of convergence is from negative infinity to infinity. That's all real numbers. You don't have to check the endpoints. There is no infinity to substitute in. And in this case, the radius of convergence would be r equal to half of infinity, which is itself infinity. Woo! That was a lot. Trying to figure out where a power series converges and diverges is a big deal. Like, it's challenging. As a matter of fact, for those of you that are here at Highline and continuing on in our curriculum, you'll probably spend a week or 2 weeks doing a dive into infinite series just to try to figure out the nuance of when a series will converge or diverge. So that is a big topic, and we just covered it in under, around an hour or so. So if you're feeling a little bit overwhelmed by that last bit, it's understandable. But deep breath, remember the big picture. A power series is just an infinitely long polynomial. It's the multi-tool of mathematics. It doesn't work everywhere. Convergence is just about trying to figure out where that power series will work. And when we say work, we mean that infinitely long polynomial. If you put a number in for x, that infinitely long sum would add to a single number. It wouldn't oscillate. It wouldn't go to infinity. It would just converge to a single number. And it's a big deal to know when something is going to work and when something's not going to work, especially, as an engineer, a computer scientist, or mathematician. It's especially valuable to know that if you're hired by a company that's got money on the line in all of this stuff. So there you have it, and I'll catch you next time.